This work is done during our research visit at Japan this summer, where I have the privilege of working with Atsushi Nintendo and Taiji Suzuki. The purpose of this talk, the topic of this talk is towards a unified analysis of neural networks in nonparametric instrumental variable regression, optimization, and generalization. Yeah, I know it's a long topic. Yeah, but bear with me, I'll show you what it means. Okay, thank you. So first, start with a little bit of background. So we know that nonparametric regression is used everywhere, every day in statistics. It's like everything you should learn if you are a statistics PhD. The first thing you should learn is probably how to do a nonparametric regression. Well, the problem with nonparametric regression is that it tends to fail when there exists like unobserved confoundings. So consider a very simple example. If you want to study the effect between like the sale of matches and the risk of getting a lung cancer. If you do a direct regression between these two things, then from common knowledge, you know, there's no connection between the two because the matches and lung are not connected. But because of the existence of like a confounder called smoking, so people who tend to smoke will buy matches, and people who tend to smoke will also get lung cancer. So it's the unobserved confounder that connects the two variables together. So the huge motivation of this talk is how do we identify the effect of matches and lung cancer, even with the existence of unobserved confounders. Okay, so yeah, so say you want to study the causal effect of smoking X on the risk of lung cancer Y. And we say there exists some unobserved confounding epsilon that affects both X and Y at the same time. A typical example of epsilon could be your gene or your occupation or childhood experience. Here we make a very strong assumption that the epsilon effect is additive. So the target variable Y is equals to H star X plus epsilon. So epsilon is only additive on Y. And because it's a confounder, so we say that epsilon is not independent of X. Okay. The problem with this non-independence is that when you take this equation, condition both sides on X, then you cannot kill epsilon anymore, right? Because you end up with like a irreducible bias, the conditional expectation of epsilon on X, which is not zero. So people in causal inference, they try a different approach. They find a new variable called the instrumental variable that only affects Y through X. A typical example of instrumental variable Z is the price of the cigarette. So we have the conditional independence between epsilon and Z, and then we condition both sides on Z, then we end up with this equation where the conditional expectation of Y on Z equals to the conditional expectation of H star X on Z. And then we don't need to deal with epsilon anymore. So through this conditioning, we kill epsilon on both sides. So this equation is called NPIV, and this is the main target of interest of this talk. Is it okay? Okay. Another example that also applies under the framework today is offline reinforcement learning. I won't go into the details of what it means, but in offline reinforcement learning, most typically your target of interest is what people call the Q function, written like this. It's like the long-term return when you take an action A in state S. And people typically estimate or solve this Q function by solving this Bellman equation of this form. We would like to point out a resemblance between this Bellman equation and the NPIV equation in the last slide, where we make the correspondence of Y is R, Z is SA, and X is S prime A prime. So what we did today for NPIV also applies in the setting of offline reinforcement learning. We want to learn a Q function. Okay. Okay. So to understand NPIV a little bit better, we do a contrasting with nonparametric regression. So in nonparametric regression, your target variable Y equals to H star X plus epsilon, with epsilon independent of X. So if we condition both sides on X, then we end up with this equation. And typically what people do in this setting is they do least square regression. So you have a model, and in our talk, we focus on neural networks. So we have a neural networks H zeta, and you find zeta star by solving this optimization problem when given access IID samples from a joint distribution PXY. Okay, so this is everyone in statistics would know. And in our setting of nonparametric instrumental variable, we have this equation, but the difference here is that epsilon is no longer independent of X, but is independent of Z. So now we solve this equation by conditioning both sides on Z. So this is our NPIV model or NPIV equation, which is different from the NPR equation that people see every day in statistics. So first problem now is that, so H star is like the target of interest. So how to estimate H star through this NPIV equation? Is everything clear? We define like T as an unknown conditional expectation operator, which maps L2px to L2pz. So it maps functions on X to function on Z. So how is defined? Defined like this. So given a function f, which is function on X, we apply T on it. It gives us a conditional expectation. And we all know that conditional expectation is a function on Z. So this is how T maps a function from X to a function on Z. And then we can write NPIV as this model, where we just plug in a definition of T here. So similar to like nonparametric regression, where you solve least squared regression, here we solve this minimization problem where instead of having H here, we have TH here. The difficulty here is that although T is called conditional expectation operator, it is actually unknown. We don't know the distribution in our model. We don't have data, so we don't know T. So how do we do this? So we do this by two-stage regression. In stage one, we kind of learn T because T is a conditional expectation. So we know from regression that all conditional expectation can be learned by regression. So in stage one, we kind of do the first regression to learn T. So this regression is written like this. So given M IID samples from PXZ, we first do this regression problem where zeta X is fixed. We solve zeta Z. So we know that H zeta Z star, zeta X, is approximately this conditional expectation, which is TH zeta X Z. Yeah.
Maybe a very silly question.
Sure.
All X, Y, and Z are observed.
Yes. So in stage one, essentially you are learning T to give a better understanding. Okay, so given T, we do a second stage regression where we solve zeta X star. And zeta X star is, we solve this least square regression problem. Here, the blue H zeta X, H zeta Z star zeta X is an approximation of TH zeta X Z. So if we plug this inside, then the stage two regression is doing this with IID samples. Okay, so this is why we need two-stage regression here. In stage one, we first learn T because T is unknown. And in stage two, we plug in the learned T and solve another regression problem. And the final estimator is given by H zeta X. Yeah, it could probably be a little bit difficult if you first come into this. And I will stop maybe a few seconds for questions. Is this okay to everyone? Yeah, I don't want people to get lost like in a problem setting. Okay, so the target of this talk is we want to parameterize, we want to use neural networks in our regression problem because we know neural networks work very well in practice. So now the stage one problem is, or just recall the two-stage problem. And the target of this talk is we want to study two aspects of neural networks in this problem setting. The first aspect is optimization aspect. So does there exist an algorithm that can find these zeta z star and zeta x star, right? We know neural networks are non-convex optimization problem. So our first target in this talk is, does there exist an algorithm, like maybe gradient-based algorithm, that can find these global optimum zeta x star and zeta z star? And if it can, then what is the iteration complexity? So how many gradient steps you need to take to find these global optimum? So that's the first question we'll talk about in this talk. And the second part I'll talk about in this talk is, provided that we have access to these global minimum, is our estimate h zeta x star a consistent estimator of the target of interest h circle? And if it is consistent, then how many samples we need for this to be a true estimator? So to be for the error to go to 0. Is that clear? So like two sides of the theory. So first side is optimization. How can we find the global minimum? And second side is like generalization. Given the global optimum, how well does it generalize to unseen particles? How well does h zeta x star actually approximate h circle? Okay. The main theoretical tool we'll use in this talk is called mean field neural networks. So yeah, because we want to do theory, you can only do two-layer neural networks, which is very unfortunate. But even two-layer neural networks are first difficult to analyze because it's highly non-convex. And two, it already performs better than fixed feature methods like kernel methods, linear regression, polynomial regression. And third, there exists a tool called mean field neural networks that allow us to do it. So I'll mainly focus on two-layer neural networks in this talk. Okay, so I'll give a few pages of background on what is a mean field neural network. So we consider a neural network, a two-layer neural network, where the hidden layer of size big N we call x superscript 1 to x superscript n, which are the n neurons. We use this big funny x to denote all the parameters in the hidden neurons, in the hidden layers. And the bold-faced x is the network input. So your neural network, a two-layer neural network, can be written as an empirical average over psi x superscript I, where psi bold-faced x is a two-layer neural network with only one neuron. And here the parameters x is W1, W2, B. So W1 is your first layer weight, W2 is second layer weight, and B is the bias in your first layer. And A is your activation function. Is that clear? The neural network. Okay.
Sure.
I will talk about it later. When you view two-layer neural network like this, and as the empirical distribution converges weakly to a population mu as n goes to infinity, then you write this neural network in the form of an integral or an expectation. This is so-called the mean field neural network, where you take the size of hidden layer to infinity, you get this perspective. Okay. The question now is, why do we want to consider the mean field limit, which I'll explain in the next slide. Is that clear? So the benefit of considering this mean field perspective is, if we just consider a standard square loss function with L2 norm regularization, like everyone would do with neural networks, we can now write the objective as a function of the distribution mu. So now objective becomes a function now from mu to r, which is, so the first term is just the standard square loss. And the second term is the L2 norm regularization. And rho here is the data distribution, like the empirical data distribution. Okay. The purpose of this, considering your objective as a function of your distribution mu, is that now f becomes a convex objective with respect to mu. It sounds like magic why you suddenly have convexity. Well, it's actually very simple, because now your function f is a composition of, because a neural network is linear in mu, right? Because it's just an integral with respect to mu, so it's linear in mu. So the composition of linear and quadratic function, which is a convex function. So that's how we get convexity. So it's just one step. We see that f is actually convex in mu. So which means that for any probability measures mu and nu, it satisfies this relation. It's like standard definition of convexity. So with this convexity in mind, then we can consider an optimization problem in the space of probability measures. So we're now doing optimization with respect to the measures rather than with respect to single hidden layer neurons anymore. So we can utilize this convexity to prove convergence. Okay. But to do optimization problem in the space of probability measures, we need a proper notion of gradient in this space, because it's not a Euclidean space anymore. What it means by taking a gradient with respect to your distributions. So fortunately, a lot of mathematicians have done it for us already. They have this notion of Wasserstein gradients, which I will not go into the details in this talk because they'll be very, very niche. So just trust me, there's a Wasserstein gradient of an objective G, which is actually a mapping from RD to RD. So the Wasserstein gradient of G at a measure mu is defined a function mapping from RD to RD, satisfies some relation. Okay. And what makes it nice is that given the simple form of f we consider, the Wasserstein gradient has a very simple form. So the Wasserstein gradient of f at the measure mu is written like this. And we consider the Wasserstein gradient at the empirical measures. So we come back to finite width neural network because we don't want to work with mean field limit, right? Because mean field limit is not the actual neural network people would use in practice. So this is the perspective we take. But in the end, we still want to work with finite width neural network. So we still evaluate the Wasserstein gradient of f at this empirical measure at the ith, like the ith neuron, which will look like this form. What makes it nicer is that the Wasserstein gradient at this empirical distribution is precisely the same as the Euclidean gradient of the loss function with respect to your hidden layer parameters up to a rescaling of 1 over n. So it sounds like magic, but actually it's all mathematics. So we first take a lifted perspective to consider an optimization in a space of measures. But then we come back to consider the optimization problem when your distribution is quantized with n particles. And then we realize that this gradient is precisely the same gradient as the Euclidean gradient of the original finite width neural network. So this means that if we study the dynamics of Wasserstein gradient with empirical distributions, it is exactly the same dynamics of doing standard gradient descent with respect to the Euclidean space up to a rescaling of your learning rate. Is that clear? Yeah.
So I just wanted to ask, I guess maybe we're going to go into this a bit later, but to get the convexity,
yeah,
this means that you could actually consider any convex objective under the L2 loss.
Yes.
Is there some benefit to the L2 loss which just makes this even nicer, or is it just because of the
It's
history of the
just simple to
Yeah, yeah.
present. Yeah. In general, it works for any convex loss, like cross entropy, logit loss, lasso, maybe. I don't know. Okay, so this is the theoretical tool. And okay, so now we consider the actual dynamics we consider for two-layer neural networks. So at iteration S from 0 to big S, for any particle I from 1 to big N, the update scheme is, so this is your particle at time S plus 1 equals to the particle at time S minus gamma is the learning rate times your Wasserstein gradients evaluated at particle Si plus some Gaussian noise at each time step. So the addition of Gaussian noise is very crucial. So this is the point where this is what the theory requires. So without additive Gaussian noise, it's impossible to show convergence. You can think of this adding this Gaussian noise as when you do like Langevin diffusion or when you do Langevin Monte Carlo, you also do this additive Gaussian noise at each time step. So when you add Gaussian noise, the effect of noise is that it can help you get out of the local minimum and can actually converge to the global minimum. Well, that's just an intuition. So that's why for a full theoretical analysis to prove convergence towards global minimum and to have very nice rate, we add this Gaussian noise in the update scheme. Then we define an entropic regularized objective, which denoted as this fancy F, which is the standard F plus epsilon times entropy. And the noisy gradient descent scheme, this descent scheme is the Wasserstein gradient descent of the color of the this fancy F. And the global minimum we want to approximate in this talk is, or at least for now, is mu star, which is defined as the global minimum of color of this fancy F. So the question we want to answer is, or want to tackle is, does noisy gradient descent scheme, so does this descent scheme can actually find a global minimum epsilon star? And if it does, what is the iteration complexity? So now we come to what assumptions we need to make on the neural networks. The neural networks we consider in this talk is bounded, okay, and has bounded gradients. So what does it mean? So it means that it works for neural networks where we consider 10H or sigmoid activation functions. It also holds for neural networks when you consider ReLU activation functions, but because ReLU is unbounded, so you have to like clip your neural network output at a certain threshold R so that your neural network becomes bounded. Okay. So these are the assumptions we make on the neural networks. Is everything clear so far? Okay. So now finally we can present the result in the background. Define H star is the output of the optimal mean field neural network, right? So this is the optimal neural network you can have, which is the minimizer of this fancy F which I showed in last slide. But this is optimal neural network. And this is the neural network we have when we train S iterations with finite width big N. So this is a neural network we consider or we use in practice. Then for any input X, we can upper bound the distance between the trained neural network and the optimal neural network with 3 terms. The first term is like finite particle error. It's 1 over n. It vanishes when you take n to infinity. The second term is like time discretization error. It arises because we are doing gradient descent rather than gradient flow. And the final is the optimization error, which goes to 0 as the number of iterations goes to infinity. And the expectation here is taken over the randomness in initial particle, initial neural network, and at the noise you take at each iteration. The thing I like to highlight here is that there's a thing called the CLSI, which is a constant, I would say, and is exponential to negative d. So this is the most annoying term in analysis, which describes the difficulty of learning mu star. So if you plug this inside, you can see this time discretization will blow up exponentially fast with respect to dimension. This is unfortunately unavoidable, and this is what people call the curse of dimensionality. This phenomenon also appears in the convergence results for MCMC, where you have, well, as long as you want to do sampling high dimensions, you have an unavoidable term that would like blow up with respect to dimensions. So this term also shows up here as well. Yeah.
Do we have any tools in the MCMC theory to get rid of them?
I don't know MCMT theory, but I don't think so.
Yeah.
Yeah. Okay. Cool. So now finally, end of background. And any questions? Okay, so now we'll consider mean field neural networks in two-stage regression. Because it's a two-stage regression, we have two neural networks to consider. Okay, so this is a stage 1 problem. This is a stage 2 problem. So in stage 1, we solve optimization problem in respect to Z. In stage 2, we solve optimization problem with respect to X. Here, HX is the two-layer neural network on X, and HZ is two-layer neural network on Z. And rho is a data distribution over X, Z, and Y. And in the sequel of the talk, to cut the notation, I will focus on the parameters X superscript I, Z superscript I, rather than the input X and Z. Because we focus on the first of the talk, we focus on optimization, where focus is on the parameters rather than the input. So I use this notation to make things a little bit simpler. Okay, so then we do the same trick. We do the mean field limit. We now have two mean field neural networks. So the mean field limit is distribution of mu x, and the other mean field distribution of mu z. And we add appropriate regularizations for both stages. So add L2 norm regularization, L2 norm regularization, and entropy regularization in both stages. So the challenge of analyzing this optimization problem is that we now have a bilevel optimization problem in the space of probability measures. If you're familiar with bilevel optimization problem, it's not that you just solve two separate regression problems and you're done. It's not like that. It's like you first solve the stage 1 problem. You plug that result into stage 2, into your gradient step on stage 2. Then you solve another stage 1 optimization problem. You plug that into stage 2, and you solve another stage 2 gradient step. So it's like an iterative process rather than two separate regression problems. So that's why they call it the bilevel optimization problem. And for fixed mu x, the stage 1 can be solved via standard mean field Langevin dynamics. Because in stage 1, as long as mu x is fixed, and just the standard mean field neural networks as are presented in the background section. So this part is considered done. The challenge is mainly in the second stage, where we have this nested dependence of mu z star mu x. Okay, then a lot of notations. So I call big F1 the stage 1 objective without entropy. F2, the stage 2 objective, again without entropy. This fancy F, stage 1 plus entropy, fancy F, stage 2 plus entropy. And now the bilevel optimization problem becomes like this. Right? I just used the notation to make the problem presented in a simpler way. Crucial observation here is that if we fix mu x, the partial Wasserstein gradients are simple. If we fix mu z, the partial Wasserstein gradients are also simple. But the nasty bit is the nested Wasserstein gradient of this mapping. So that's where the nasty bit comes in. So how to avoid this? Well, we focus on, so this is our bilevel optimization problem. We first write it as a constrained optimization problem, where the stage 1 problem is written instead as a constraint on stage 2. So this is your stage 2 objective, but you do this optimization under this constraint. So this constraint ensures that when you solve stage 2, your mu z is actually close to your stage 1 solution. And when epsilon is 0, you recover the original bilevel problem. Similarly, we can write it as a Lagrangian optimization problem. We write it like this, where this hard constraint is written like a penalty term on the stage 2 loss. And when lambda goes to infinity, it recovers the bilevel optimization problem. But in practice, we cannot take lambda to infinity, so we have to take into account an additional approximation error because of using lambda not equal to infinity. Okay, so this is our objective. Our first proposition is to let mu z star mu x be the solution to stage 1 optimization. And I've said it's easy because it's standard linear Langevin dynamics. Then what's the standard gradient with respect to the first objective and the second objective are all simple. You can see that we mysteriously get rid of the nasty mapping, right? So we don't need to take the gradient with respect to this mapping. The trick here is that because mu z star mu x is defined as the optimum of f1, so if you take the gradient of this mapping by the chain rule, the second term is just 0, right? Because it's already at the optimum. This is what people call the envelope theorem. So when you take the gradient of this mapping, you only need to take the gradient with respect to the first argument. And you don't need to involve the gradient with respect to the second argument. So that's how we, with this Lagrangian formulation, we'll get rid of the nasty nested mapping. Okay. Then we want to analyze the convexity of our objective. Yeah, because convexity is everything, is all we need, or is the most crucial bit we need for analyzing convergence. So we need to analyze the convexity of this objective. The first observation is that the partial mapping mu z to this is convex for any fixed mu x. But the partial mapping of mu x is to this mapping is not convex. And the joint mapping is also not convex. I won't show the details, just trust me, we only have partial convexity here, but not convexity in this guy and this guy. So how do we exploit this partial convexity bit? So we exploit this property by doing this double loop optimization problem, where in the inner loop, we first solve this optimization problem, like in the stage 1 problem. You know, it's easy because it's just standard linear Langevin. And then we solve this problem with fixed mu x. So this is again easy because of convexity. And then in the outer loop, we solve this optimization problem, which is like the most nasty bit we are going to solve in the outer loop. So it's like we first do the simplest bit, right? We have convexity f1, we have convexity, partial convexity on lambda. So first solve the easy bit to make the problems a bit simpler. Then we deal with the nasty bit and see what we can do with the nasty bit. And our algorithm is the same. We do noisy gradient descent as mean field neural networks. Yeah, sorry, I probably got a bit fast. Are there any questions so far? Yeah.
So like for the outer loop, it's still optimization problem, right? Like I'm not sure whether it's convex or not, because in the inner loop, it's absolutely a gradient descent on the convex function.
Yes.
But for the outer loop, it is not necessary to be, like you said, it is not convex with respect to.
No, it's not convex.
Yeah.
But I will still prove convergence, even it's not convex, by doing some extra technical tricks.
So
I will show later.
you still apply the gradient descent, even
Yes.
if the optimization problem is not convex, but you can still apply it to do the optimization.
Yeah, algorithm is also fine, right? You can apply gradient descent on any objective, regardless of it's convex or not.
Oh.
It's just that when you want to prove theory, you want to show convexity. And what I'm going to show next is that even if the outer loop is not convex, I can show it's weakly convex, and I can have some extra tweaks to still prove convergence results. Okay. Okay, so now here's the inner loop. It's easy, and yeah, I'll skip it because of the time. It's just standard noisy gradient descent. So big T is the number of iterations we take for the inner loop. Alpha and beta are the respective step size of the inner loop. Sigma 1 is the amount of Gaussian noise you add at the inner loop. Okay. And all these Wasserstein gradient I just showed you, they are easy to compute because they are just partial Wasserstein gradients and no nested mapping is used. Okay, then our assumptions. So we still want the same assumptions as mean field neural networks. We want bounded neural networks, bounded gradients, bounded neural networks on X and Z, and bounded gradients on X and Z. So it works for two-layer neural networks with 10H and or ReLU, plus if it's ReLU, then we need a smooth output clipping. And second assumption is that we exist a universal constant such that the target random variable is bounded, and the H star X is also bounded. You may wonder, oh, you assume target random variable, then it doesn't work for regression. But we just make the assumption for simplicity because the boundedness of Y can be easily relaxed to a sub-Gaussian noise. Okay, so this is the inner loop convergence. So given, I'll just skip it. Yeah. Okay, so now we come to the interesting bit, the outer loop.
Sorry, Hudson, the
Yeah.
inner loop convergence, basically what you're going to show is it's the same rate as the normal mean field.
Yes. Okay, then it's the outer loop. So we want to solve this optimization problem, right? We write this fancy L into a standard L plus entropy term. And again, by the envelope theorem, if we take this Wasserstein gradient, then we only need to take the gradient with respect to first argument. So we only need to take gradient with respect to mu x. Yeah, I know it. Mu x. We don't need to take gradient through the nested mapping. And the algorithm is here. The algorithm is the same. So sigma 2 is the scale of Gaussian noise at each iteration. Gamma is the step size, and we have nx particles. Okay. We call our algorithm a fully first order bilevel MFLD, but it's a silly name. Don't care about it. Okay, so now we have the algorithm. So what about the theory? So the major question is how we can prove convergence of the output of our algorithm towards the optimal distribution. And the key is convexity. But unfortunately, we can only show weakly convex. So suppose assumption 1 holds, then we have this lower bound, negative lower bound on the Bregman divergence of L lambda. So to give an intuition of what is Bregman divergence, so the Bregman divergence is like a linear approximation of a function at time x0. So if the function is convex, then the Bregman divergence is this red little gap here. If red little gap is positive, then you know the function is convex because it's always above your linear approximation. But unfortunately here we only have a negative lower bound, so it's only weakly convex. But still, we managed to prove convergence by introducing some little c here. So let c be some arbitrary constant here, and assume that sigma 1 or sigma 2 times c is larger than this guy. Suppose the step size is small enough, then for a fixed lambda, we have this upper bound on hs. The first term is the iteration term. So as the number of steps it goes to infinity, the first term goes to 0. Second term is the particle approximation error. As you have infinite particles, then this term goes to 0. This term quantifies the contribution from the inner loop. So that this 2 fancy KL represents the inner loop error. So it's understandable that the inner loop error will also contribute to the outer loop, to the final convergence, right? And this guy is the time discretization error, same as standard mean field. And we have an extra term that involves C here. This term arises because we don't have weak convexity. And define H lambda star as the optimal mean field neural network, and define HS hat as the output of our final algorithm. Then we can prove this. The bound on HS controls this difference between our neural network and the optimal neural network. Yes.
I don't know if I'm going to spoil anything, but like, did we get tighter bounds by not having a fixed lambda and having lambda grow as a function?
Yes, it is possible. Yeah, but then yes, it is possible. Yeah, it's something I want to do. Yeah, but in the end, it's I'm just too lazy. I don't want to introduce more notations. Yeah, just crazy this paper is. So the optimization bound wants a small lambda, right? It makes sense. So now finally optimization bit is done. Now we have another bit is the generalization. So how well does the optimal neural network approximates the H circle given RID samples, right? So here we consider M RID samples in stage 1 and N RID samples in stage 2. We write our objective with respect to the empirical average over M samples and the samples in 2 stages. And recall that our conditional expectation operator T is this guy. Okay? And then we make assumptions on the well-specifiedness of the problem. So first make assumption on H circle. So first say that H circle can be expressed as a mean field neural network. So this is like a well-specified condition. We say that our target variable lies in the hypothesis space we're considering. And the assumption 4 is similar. So it says that the conditional expectation operator T, after acting on a mean field neural network, lies in another mean field neural network. Yeah, these are like well-specified conditions. Okay, then we have a generalization bound. So suppose these conditions hold fixed and lambda, let it to be the optimal neural network. And then with high probability, the difference between the optimal neural network and the truth can be bound by these guys. So this guy and this guy goes to 0 as n goes to 0, goes to infinity. This is expected because we have 2-stage problem, so we need both stages, the samples of both stages to have go to infinity, so we can drive the total error to 0. We have additional term that's proportion to 1 over lambda, because essentially we want a large lambda, so Lagrangian problem was faithful to original bi-level optimization problem. Yeah, because we work with finite lambda in practice, so we have additional error which comes from lambda. And mx and mz is the size of the hypothesis space you're considering. You have a larger size, you have larger error. You have a smaller size, you have small error. Finally, there's a trade-off on lambda, sigma 1, sigma 2 in terms of optimization and generalization. So the optimization bound is like this, and generalization bound is like this. Unfortunately, there does not exist a pair of lambda, sigma 1, sigma 2 that both error would vanish, finish very soon. Finally, run our algorithm on an offline RL's benchmark, and we compare with another algorithm using neural networks, and we can see we have slightly better results. We have a more stable training trajectory, mainly because we only use fully first-order gradients in optimization problems, while the DFIV, as presented here, uses second-order information, so the training trajectory is much less stable. Okay, so that's the end of the talk. Thank you very much.